Yeah, so this is a kind of a nifty locus. I'm playing with triangles that are interscribed between an outer ellipse, this black ellipse here, and have a fixed circular caustic or a fixed incircle, right? So the blue triangles are Poncelet triangles in such a situation, and this app allows me to visualize loci of triangle centers. Here I'm focusing on a particular locus on ETC labeled as X36, and X36 is the inverse or the inversive image of the in-center, which is fixed in this family, labeled here as C, so X1 is fixed, in the circumcircle, which is this dash blue circle here. So X36 is such an inversive image. So I have a fixed point, C, which is being inverted against this moving circumcircle, whose radius, you can see the radius, the circumradius out here, is variable, and whose center, the circumcenter, X3 over here, sweeps an ellipse. And we saw in previous videos that this ellipse had this very nifty property of having its foci railed onto the axes of the outer ellipse. Now, it's quite remarkable that through this process of inversion, X36 is actually sweeping a circle. This red circle up here. If I move the center or the in-center of this family, or C, I get circles or circular loci of different radii, right? So if I'm now just sliding my C horizontally, you can see how that locus changes. And by the way, I'm drawing this line that connects the circumcenter to the triangle center X36. So you can see that the center C, which is being inverted with respect to the circumcircle, is collinear with these two endpoints, right? So as expected, when you invert a point, in this case C, with respect to an inversion center, the inversive image must be collinear with those two. So I'm drawing that line there. Now I can now observe what's happening to the circle, and if you play enough with this, you're going to see that there is this eversion thing that takes place when C goes through a particular region. So what do I mean by eversion? The locus becomes this very high radius circle, and at some point it everts into a circle that is basically oriented in the opposite way. So let's look at this phenomenon of eversion. Here's the eversion of that circular locus, right? So I'm playing around with the incircle of the family, or C, and I can see that there's a region for which the circle inverts. Now it turns out that this region, if I can bring the system back to view here, okay, is precisely the one where we had calculated before. This green curve here, ellipse-like curve, which has the property that if C is on it, right, if the center of the caustic is on it, okay, right, like so, the locus of X3 is going to pass through it. In fact, one of the vertices of the locus of X3 is going to be C. And the reason that it's a vertex of the locus is because the major axis is pointed at C in general, right? The major axis of X3 is always pointed to C, as we can see here. So it turns out that the region of eversion, the locus of C, such that you get an eversion. In fact, what happens at this point is that the locus of X36 is a straight line, is precisely that region for which C is a vertex of X3. When C is interior to that green region, for example, like so, okay, we saw in a previous video, and by the way, this green curve is computed numerically now, we saw that C is now interior to the locus of x3. And in this case, what we get is a locus of x36, circular locus, that gobbles up the system, right? So the system now, the Poncelet system is now interior to that, provided that C is interior to that region. When C is on that region, now let me play with that, is on that region, x36 becomes a straight line, and when you move out of that region, then you get this outer circle phenomenon, okay? But it's quite remarkable that the inversion of a fixed point, C, or the in-center of that family, with respect to a moving circumcircle of variable radius, okay, results in a perfect circle. So we don't have a proof for that. It could be simple, but we thought this was quite a remarkable property for these Poncelet triangles inscribed in an ellipse and circumscribing a circular caustic, i.e., whose in circle is fixed. So I'll let you watch this for a little bit. I'll move C a little bit down, actually a little bit up, right? So that the locus becomes smaller. All right, I'll see you on the next video.